To determine if the flow is in turbulent or laminar, we need to just first of all specify and calculate the Reynolds number. You know the Reynolds number is a dimensionless parameter. The Reynolds number can be calculated in this equation as like equal to rho Vd over mu, or if we're just gonna substitute rho mu over rho with the like the nu, we can write Vd over nu. And you know this formula, D is like the pipe diameter, and rho is the density of the liquid. Mu is the dynamic viscosity, and nu, this one, is like a kinematic viscosity, and v is the mean velocity. So either we're just going to use the formula with the mu dynamic viscosity or with the nu dynamic kinematic viscosity. You can calculate a Reynolds number. Based on the Reynolds number value, we can determine if the flow, if for example, if it is like the pressurized system or like the pipeline, if it is like less than 2000, we can assume that the flow is like a laminar, is like a low flow, a low speed flow. If the flow is like the over 1000, 4000, we can say like the turbulent flow. And in between 2000 and 4000, we can say this is like a transitional flow. The same situation, the limits for open channels, the Reynolds number is less than 500 is a laminar, greater than 2000, we call like the flow in open channel is a turbulent, and between 500 and 2000 is a transitional flow. So let's discuss about more details about like this laminar flow and its characteristics in detail. So the laminar flow, we know that the head loss is proportional with the velocity, directly with the velocity. However, in the turbulent flow, the head loss is proportional with the square of the velocity. So let's just look at the laminar flow. In the laminar flow equation, is because of like a friction. We have this equation. This equation is for the laminar flow situations. It's like an empirical equation we can just derive. And the general equation of the head loss due to the friction, we can have this one, HF is lambda L V squared over 2GD. If we equate the right-hand side and simplify the equation, eventually we can get and replace a Reynolds number, rho Vd over mu or Vd nu, in this kind of like the resultant equation. We can get the formula as lambda is equal to 64 over Reynolds. So this is like the indirect relationship between lambda and Reynolds for the laminar flow. In addition to that formula, Blastus in 1930 derived the equation for the smooth turbulent pipe friction, that the viscosity has got a proportion effects that dominates with the like the lambda is an indirect proportion with the Reynolds. However, in the rough turbulent pipe friction, both viscosity and pipe roughness has an impact on the like the to calculate the pipe roughness coefficient. And for the smooth turbulent, Blastus just calculated lambda is equal to these equations, like the 0.316 over Reynolds raised to the power 0.25. Or in some references, if you're just gonna in the UK, like the reference books, if you're just gonna replace like the lambda is equal to 4f, okay, f is equal to 0.079 divided by Reynolds raised to the power 0.25. The Reynolds and its order is exactly the same for both equations. Just pay attention; these two equations are completely the same. The only changes is that lambda has been substituted with 4f. If you just replace lambda with 4f, you know, and both sides divided by 4, left-hand side is equal to f, right-hand side, if you divide this figure, 0.316 by 4, you will get that value. You know, just to show you how it works, 0.316 divided by 4, this is the value on the right-hand side. And the Reynolds is exactly the same. You can write divided by rho raised to the power 0.25, or you can say directly Reynolds raised to the power minus 1/4 is exactly minus 0.25. However, for a general equation, you can just like another type of equation, general form of the equation derived by Kohlberg and White. It's a popularized Kohlberg and White equation and applies for all ranges of the turbulent flow. It's not only for the smooth or rough. You can just use it for any kind of like the turbulent flows. And you can see here, it's an implicit equation from lambda. Implicit equation because lambda is located on the first, on the left and the right hand side. You know, on the left hand side, it's not like a direct equation to calculate lambda. The way that we can calculate this equation is by using the trial and error or some other like the numerical methods that we're just going to go through in here in some examples in this chapter. So on the left hand side is a 1 over square root lambda under is equal to minus 2 log at the base 10. Inside the bracket, you have like a 1 term k over d is a relative diameter or relative roughness. Relative roughness because the k is the physical roughness or the height of the protrusion. You can see here if the roughness in the pipe looks like this one, and the average sticking out or the protrusion is k, you can call it like a physical roughness. Physical roughness divided by the d, we can call it like the relative roughness, and d is the diameter of the pipeline. Okay, so k over 3.7 times d plus 2.51 divided by Reynolds times square root lambda. Lambda you can see if it's located on the left and right hand side. So if once you're just gonna like solve this equation for lambda, we can just, for example, one like the simple method is that you can assume like one lambda on the right hand side and calculate the lambda on the left hand side, and then replace it as long as the lambda on the left and right becomes converged. In this equation, if you're just gonna substitute HF, I mean, if we can use HF is equal to lambda L V squared over 2GD, if we replace some terms with specifically with the some terms with this kind of like equation in the main equation, we can derive an equation based on to calculate the velocity here. Just compare between these two equations and see how we can just replace that kind of like the values in this equation to just get to this value. So the velocity in this equation is equal to minus 2 square root 2GD SF, where SF is the hydraulic gradient. Hydraulic gradient is equal to HF divided by L. So you can see here, if you just divide both sides by L, on the left-hand side, you have HF over L or SF. SF can be calculated and SF can be substituted in the top formula, in the right formula. If you're just gonna get to this one, you need to just substitute the Reynolds with the values, like the VD over nu, and then replace V from this equation and just go and calculate the rest of that. And then, so this is an equation that we can have minus 2 square root 2GD SF log and the base 10 K over 3.7 D plus 2.5 nu. It is the dynamic viscosity divided by D square root 2GD SF. So that's the equation that we're just going to have if you need to just directly calculate the velocity. The next one, you can either use the lambda pipe roughness coefficient by using any of these equations for the smooth turbulent from this equation, or general form from the Kohlberg-White. Kohlberg-White is a very popular equation that we can just normally use it to calculate the lambda. In parallel to calculate lambda by using any of these equations, you can just use the a diagram. It's called like the Moody diagram. Moody is the person who derived or developed this graph or the diagram. And in this diagram, we can have we are able to calculate the lambda for different types of the flow. For example, let's look at the diagram, all the sections. Like the horizontal axis is the Reynolds number, changing from 1,000 to 100 million Reynolds, like the number. Vertical axis on the left is a friction factor or pipe roughness coefficient, lambda, which is going to be calculated as a result of this graph. And you can see on the right hand side there are like a lot of like the graphs here, and each graph is relevant associated with a specific relative roughness, or K over D. K is the absolute roughness, or like the height of the average height of the protrusion, or the sticking out average of the sticking out of the pipe inside the pipe, divided by the diameter. So it's called relative roughness as well. So you're just gonna range from this kind of like a figure 0.00001 up to like the 0.05. So you can choose any of these values here, and then you can just, if you have a Reynolds number, the intersection of the Reynolds number with that kind of like the graph, if you can find that point and go to the left hand side, you can easily find like the friction factor or pipe roughness coefficient of lambda. And this is like the things that we're just going to calculate here. And the top is exactly the same as the bottom. The top horizontal axis is the Reynolds number. And just pay attention, in some other references, you might see like instead of lambda, they're just going to use F. If the reference is the UK references, normally F is like the relationship between F and lambda. Lambda is equal to 4F. 4 times F, and if the reference is the like American like the reference, normally lambda is exactly replaced with F. So just bear in mind. So in the next presentation or next like the video, we're just gonna have a look at some of the examples in this kind of like the section and chapter.